In this example problem, we're going to design the below beam. We will assume that we have already found our slab thickness to be 8 inches, and we're going to assume that the beams are simply supported. So we can see that this is a one-way slab on beam system. So we're going to design our beams to be T-beams. So we will include some width of our slab. Our slab will make up the top flange, and then our T is going to drop down and be the depth of the beam section. We can see that our beam length or span length is 24 feet, and our slab span length is 16 feet. And as I said before, our slab thickness is 8 inches. So we'll use all of these values moving forward in the design. Our first step is going to be to choose the dimensions of our T-beam based on ACI 318 provisions. The first thing we need to do is decide on our flange thickness. This is easy because we know that our flange is equal to our slab thickness, which we would have found in our slab design to be 8 inches. We were given in this example. So then we can find the minimum height of our overall beam. And we're going to use the ACI minimum height requirements for simply supported beams. And remember that these are based on deflection requirements. So our span length is 24 feet. We take this times 12 inches per foot divided by 16 gives us a minimum height of 18 inches. So we're going to use the rule of thumb we'll start with a beam depth in inches equal to our span length in feet. So we have a 24 foot span, so we're going to try starting with a 24 inch deep beam. So this will be our height of our beam to start. So then we can find the depth of our steel. We're going to assume that we have a T-beam with 2 layers of steel in the bottom. So the depth is to the centroid of these 2 layers. So our depth is going to be H, which we just found to be 24 inches, minus our cover is 1.5 inches for interior exposure. We're going to assume that we have number 4 stirrups. We'll need to come back and check that assumption when we do our shear design. So number 4 stirrups have a diameter of 0.5 inches. And we're going to assume number 8 bars for our longitudinal steel. So we'll need to come back and check that after we design for our longitudinal steel. And our spacing is 1 inch or our bar diameter. So we'll have 1 inch there. So then we'll have our D equal to 20.5 inches. So we can next use the rule of thumb, and we'll say that our base width is about equal to 0.5 D. So 0.5 times D is going to be 10.25 inches. So I'm going to round up here, and we'll use a web width of 12 inches. So then we can find the spacing between our webs. So we remember that our T-beams are part of an integrated slab system. So to find the width of our top flange, we need to know the spacing between the webs. And the spacing between the webs is just going to be equal to the length of our slab minus BW. So in our case, the length of our slab is 16 feet. And our web width is 1 foot, 12 inches. So we have 15 feet, and we're going to change this into inches. So 16 minus 1 times 12 is 180 inches. So then we're ready to use our ACI expression to determine our flange width. So plugging in our values, we'll have 8 times the height of our flange, which is 8 inches. So this will be 64. We'll have half of the spacing between our webs, so half of 180 will be 90 inches. And then our ln over 8 is 24 feet times 12 inches per foot over 8, and this is going to be equal to 36 inches. So 36 inches is our minimum, so that's what we'll use to find our BF. So our BF then is equal to 2 times 36 inches plus our BW, which is 12 inches, which will give us a BF of 84 inches. So we now have all of our preliminary dimensions for our preliminary design. We'll next need to compute the required AS, and then we'll select the number of bars and the size of the bars to use in our design. So we were given a dead load and a live load that included, in this example, included the self weight. So we're just going to use these loads exactly. So we have a dead load of 2 kips per foot plus 1.6 times our live load, which was given, which was 1 kip per foot, which will give us a total load of 4 kips per foot. So this is our factored ultimate load. So then we can plug this into our moment expression for a simply supported beam, the maximum moment at midspan. So we'll have our WU, which we just found, 4 kips per foot, times our length, which is 24 feet squared, divided by 8, to give us our M sub U, which is 288 kip feet, times 12 to give us kip inches of 3,456 kip inches. So then we can find our MN required. So our MN required is MU, so we just found it, 3,456 kip inches, divided by our phi, which we're going to assume tension controlled behavior. We're going to need to come back and check it then, but we'll assume it initially. So we'll have a phi of 0.9, which will give us an MN required of 3,840 kip inches. So then we can find our AS required, and to do this we will use an approximate lever arm, 0.9D, which will give us an expression for an approximate nominal moment capacity. And we can find our AS required. So we'll have MN required 3,840 kip inches divided by our FY, 60 KSI, times 0.9, times our D, which we found to be 20.5, assuming our number 8 bars. So then we'll get an AS required of 3.47 square inches. So we can take this 3.47 to a design aid and see what number of bars, or what size of bars and what number of bars would be best for this case, or we can just use our knowledge of the bar area and come up with a try. So I'm going to try using 4 number 9 bars. And this is going to give us an area of 4 times 1 square inch, so 4 square inches. So we're going to use this moving forward. So next we need to recalculate our D using our diameter of our number 9 bars because we had initially assumed a number 8 bar. So our H here is 24 inches minus our cover, 1.5 inches, minus the diameter of our stirrup, which we're still assuming number 4 bars, minus the diameter of our number 9 bars, 1.128, minus half of our spacing, 1.128. And this will give us a D equal to 20.3 inches. So now we have our area of steel, and we have our depth of that steel. We'll next quickly check to make sure that we have more steel than the minimum steel requirements from ACI. So our minimum steel requirements are the max of these 2 expressions. So we have 3 square root of 4,000 psi divided by 60,000 psi times 12 inches times our D, which we just found, 20.3 inches. And then our other expression, 200 divided by 60,000 psi times 12 inches times 20.3 inches. And we'll get these values to be 0.77 square inches and 0.81 square inches. So we can see that the maximum of these is 0.81. So we need at least 0.81 square inches, which we have 4 square inches, so we're okay here. We'll next need to determine A and check our steel strain. We're going to start by finding our beta 1. And for us, we have, again, 4 KSI concrete. So our beta 1 is equal to 0.85. And then we can plug all of our values in and find C. So our AS is 4 square inches. Our FY is 60 KSI divided by 0.85. We have 4 KSI concrete. Our B we found is the width of our top flange is 84 inches. So remember that's the width of our top flange that we found in an earlier step. And then our beta 1 is 0.85. So we then find our C to be 0.99 inches. We can use this to find our A. So 0.85 beta 1 times 0.99 gives us an A of 0.84 inches. So we can compare this to our flange height, and we see our flange height is 8 inches. So we know that our compression block lies entirely in our top flange. So in our cross section, our compression block will be in our top flange. So we can analyze it just like a rectangular beam. We'll next need to find the distance from the top compression fiber to the centroid of the bottom layer of our steel, which we'll call D sub T. So this will be our H, 24 inches, minus our cover, 1.5 inches, minus the diameter of our stirrup, 1/2 inch, minus 0.5 times the diameter of our longitudinal bars, 1.128 inches. And this will give us a D sub T of 21.4 inches. We can use this value and plug it in to find our strain. So we'll have 0.003 times 21.4 minus 0.99 divided by 0.99. And this will give us an epsilon t of 0.062. And we can see that we are greater than we're greater than our tension controlled limit of 0.005. So we know we're tension controlled, and we're okay with our initial assumptions with phi. We're now ready to find our moment capacity. So just plugging into our nominal moment capacity expression, we'll have 4 square inches of steel. We'll have 60 KSI steel times our D, 20.3 minus our A, 0.84 divided by 2. And we'll get a nominal moment capacity of 4,771 kip inches. So then we can find our phi mn is 0.9 times 4,771. And we'll find our phi mn to be equal to 4,294 kip inches. We can now compare this to our m sub u, our ultimate moment, which we found to be 3,456 kip inches. So we can see that our phi mn is greater than or equal to our mu. So our section has sufficient capacity to hold our ultimate loads. We can now check our detailing. And first we can find our spacing. So our spacing is the max of dB, 1 inch and 4/3 times the aggregate size. So here we have our dB controls, so we'll have a max of 1.128 inches. Our bend diameter of our number 4 stirrups here is 4 times the diameter of the stirrups, so 4 times 0.5 inches is 2 inches. So now we can plug all of our values in and do our 2 ACI checks to make sure that our steel will all fit into the width of the beam. So here we have 2 times our cover, 1.5 inches interior exposure, 2 times 0.5 inches diameter of the stirrup, plus we have 2 bars, 1.128 inches in diameter, plus 1 space at 1.128 inches. And we'll find this is equal to 7.4 inches, which is indeed less than our BW of 12 inches. So we're okay in our first check. So our second check, we have 2 times our cover plus 2 times our stirrup diameter plus the diameter of our bend plus n minus 1 times the diameter of our longitudinal bars plus n minus 1 times the diameter of our longitudinal bars, which will equal 8.3 inches, which is again less than our BW, equal to 12 inches. So our second check is okay. And that concludes this design example. Here is a drawing of our final design with our 4 number 9 bars, our 4 KSI concrete, 60 KSI steel, and our overall section depth and the top flange width. So remember that this is part of an integrated slab system. So our slab would actually continue in each direction. But this 84 inches is the width that we can count in our design here.